Hi students, in the last video we have discussed about the cell reaction, cell notation as well as a single electrode potential, standard electrode potentials, in that standard electrode potential, standard oxidation potential as well as the standard reduction potentials, and along with that we have also discussed about cell potential, that is EMF of the cell. And in today's class, that is lecture number 3, we'll start with a standard hydrogen electrode, SHE, or its another name is a normal hydrogen electrode. Okay, before we're going to start a standard hydrogen electrode, once again just will recall our Daniel cell. You know that in Daniel cell, one side we have taken a zinc electrode and other side we have taken a copper electrode. And when both electrodes are connected to each other, then here the difference in electrode potentials of these zinc and copper experimentally calculated, it is 1.1 volts. Means we can calculate only difference of electrode potentials when they are connected to each other. First we have to know that point. Now we'll discuss some examples. Say only zinc electrode I have taken, individually zinc electrode I have taken. Means zinc rod has dipped in 1 molar zinc sulfate solution. And of course when zinc and ZnSO4 connected to each other, then here some potential has developed. And here how much potential has developed is just impossible to calculate. Similarly, here copper rod has dipped in 1 molar copper sulfate solution. Here also how much potential has developed is absolutely impossible to calculate. Similarly, here how much electrode potential has developed in silver electrode is not possible to calculate. Why? Because we have taken only single electrodes only we have taken. Only zinc single electrode, it is only copper single electrode, here only silver single electrode. Means the absolute value of electrode potentials of single electrodes are not possible to calculate. But the thing is, here generally we will write E naught, a reduction potential of zinc will write minus 0.76 volts, as well as E naught Cu plus 2 oblique Cu, copper reduction potential value will write plus 0.34 volts. Like that we'll write values of various electrodes reduction potentials. Now question arises, how these values are obtained? Just now we have discussed that it is not possible to measure, it is not possible to calculate electrode potentials, and exactly it's below we have written its value. And here also, it is not possible to calculate electrode potential of this copper, and it's below we have written its value. Then question arising, how these values are obtained? For that purpose, what we have to do means this electrode, or this one, or that one, anyone, these electrodes should connect to one reference electrode whose potential is already known. This electrode or this electrode or even a silver electrode, whatever it may be, these electrodes should connect to another electrode and its potential already known. That another electrode only considered as a reference electrode. Here, according to UPSC convention, that reference electrode is nothing but a standard hydrogen electrode. This standard hydrogen electrode is considered as a reference electrode and whose potential is assumed as 0 volts. Remember, it is not calculated, it is just assumed as 0 volts. Right. Now, we'll just discuss how to construct a standard hydrogen electrode. For that purpose, see how zinc rod has dipped in zinc ions contained solution, how copper rod has dipped in copper ions contained solution. Here also what we have to do, hydrogen we have to dip in hydrogen ions contained solution. That's why in hydrogen ions contained solution I have taken HCl, there is no problem in that. But the thing is, hydrogen is absolutely a gaseous substance. How to dip hydrogen gas in HCl solution is a big question mark. Then, to overcome this problem, we have to use some inert electrodes like platinum. Platinum we have to dip here. What is the meaning of inert electrode? Means that platinum is not able to react with this HCl. Then, if a platinum is dipped in HCl solution, of course it is not considered as standard hydrogen electrode. Why it is not considered as standard hydrogen electrode? Means there is no any contact of hydrogen gas as well as HCl. Now what we have to do on this platinum rod, we have to pass hydrogen gas. Then only it is acting as a hydrogen electrode. And it's a clear explanation. Now we'll discuss in this diagram. It is absolutely standard hydrogen electrode diagram. Here in one container we have taken 1 molar HCl solution has taken. Because we are measuring a standard electrode potential, we are measuring, that's why concentration should be 1 molar. And we are maintaining a 298 Kelvin's temperature also we are maintaining, right? Now in that HCl solution, we have taken one platinum foil. Platinum plate has to take and on that platinum plate, we have to coat with finely divided platinum only. Like powder platinum we have to coat on its surface for better absorption purpose. Now that platinum plate has to be welded to one copper wire, and it is one outer jacket. From that outer jacket, hydrogen gas we are passing on to this platinum foil. Then hydrogen gas molecules will absorb on this platinum foil. Now this platinum foil, nothing but a hydrogen gas, because hydrogen gas molecules are absorbing on this foil. That's why hydrogen is in contact with HCl solution. Just like how zinc rod has contacted with the ZnSO4 solution, similarly hydrogen gas has contacted with the HCl solution, nothing but H plus ions. Here some potential is developing. That potential is assumed as 0. It is not a calculated value, it is assumed as 0 volts. Right. Now, our SHE, and before that, here hydrogen gas we are sending on that, and that hydrogen gas is coming and absorbing, and excess hydrogen gas is going from the outlet. Excess hydrogen gas is going from the outlet, of course. Now, our SHE can act as both anode as well as cathode. Now, if SHE is acting as anode, oxidation is taking place. If our SHE is acting as cathode, definitely a reduction will take place. Now, we will write both anodic reaction as well as cathodic reaction of SHE. Right. If it is acting as anode, therefore at anode, what happens? Let's see. Anode is nothing but oxidation takes place. Oxidation is nothing but loss of electron. Our hydrogen gas by losing electron converted as H plus, whose concentration is of course 1 molar, and it is not balanced. That's why here we are using half. Here loss of electron or increase in oxidation state. That's why this is a reaction of oxidation only. Now we can show it's a symbol, electrode potential symbol like this. E naught, H2 converted to H plus, that's why half H2 oblique H plus I am taking. And H2 gas, we are sending at 1 bar, and H plus concentration is 1 molar. And its potential, it's a standard reduction, it's a standard oxidation potential is assumed as 0 volts. Because it is a symbol of oxidation, and it is an oxidation reaction. And a reaction is taking place at anode. That's why it is nothing but a standard oxidation potential SOP. Similarly, our SHE can also act as a cathode. That's why at cathode, here an anode oxidation takes place. At cathode, obviously reduction takes place. That's why it's just a reverse reaction only. H plus by taking one electron converted as H2. And due to reduction, we can say it is a cathode. And we can also show a symbol, a reduction potential symbol, that is E naught. And just will write a reverse sign, H plus oblique H2. And H plus concentration is 1 molar, and the gas we are sending at 1 bar. And its potential is also 0 volts only. And here reduction takes place, that's why it is a standard reduction potential. It is a standard oxidation potential. Means that is, it may be standard oxidation potential, or it may be either standard reduction potential. Its value will be 0. Therefore, by merging these two equations, we can write one reversible reaction. For that purpose, we can use this one or this one. I'll use this one. say H plus electron converted to H2. That means here of course concentration is 1 molar and at 1 bar pressure. See here, oxidation is possible as well as reduction also possible. Forward reaction is possible as well as backward reaction also possible. That's why I am just showing with a reversible sign. Okay, that's why our SHE is considered as a reference electrode. With the help of this reference electrode, we can calculate reduction potentials of all electrodes. Now question arises here, how to calculate standard reduction potentials of remaining electrodes. For that purpose, we will discuss now how to calculate zinc potential value as well as copper potential value, etc. Okay. Now, we'll discuss about E0, standard reduction potential of zinc electrode only. Zn plus 2 oblique Zn I am taking. Why? Because it is a reduction symbol, means we are calculating a standard reduction potential of zinc. Now, here very important point is, according to our NCERT book, whatever the electrode may be, whose potential to be calculated should connect with SHE. In that important point, in that our SHE always we have to keep at the left side only, means our SHE is always acts as anode and the electrode whose potential to be calculated is always should act as cathode. It is very important point. That's why now I am taking the zinc electrode at the right side of this SHE only. See here. Now already SHE diagram is there. Now zinc electrode diagram will just see that. It is a zinc rod, has dipped in 1 molar zinc sulfate solution of course. And both this SHE as well as the zinc, both we are connecting externally through the potentiometer. Right. Now internally both are connected to each other with salt bridge as usual. Right. When SHE as well as zinc, that is a standard hydrogen electrode as well as zinc electrode, both are connected to each other. With the help of potentiometer equipment, we can measure experimentally potential difference. When both are connected to each other, how much potential difference existed means that is minus 0.76 volts. This value obtained purely experimental basis. Now, what is our main aim? We have to calculate a standard reduction potential of the zinc. For that purpose, again we will use our EMF, that is a cell potential formula. Already we have learned in the last video. That is a E0 cell. E0 cell, nothing but EMF is equals to E0 cathode minus E0 anode. E0 cathode minus E0 anode. Then how much cell potential is developed here due to, when both are connected to each other, minus 0.76. That's why minus 0.76 is equals to E0 cathode. Then which electrode is acting as cathode? Zinc electrode only acting as cathode. That's why E0 Zn plus 2 oblique Zn minus. Then which electrode is acting as anode? Definitely SHE only acting as anode. Therefore E0 I am taking directly SHE, standard hydrogen electrode. Next, minus 0.76 is equals to E0 Zn plus 2 oblique Zn minus 0, because SHE value is assumed as already 0. Therefore, then we will write finally E0 Zn plus 2 oblique Zn value minus 0.76 volts. Like this, we can calculate all standard reduction potential values with the help of our standard hydrogen electrode. Then here one important point we have to observe, that is here SH value, E0 SHE value, standard hydrogen electrode value 0 volts, as well as E0 zinc electrode value. E naught Zn plus 2 oblique Zn value minus 0.76 volts. If you observe both the values, whose value is bigger? Definitely SHE value is bigger. Means here zinc value is smaller. When both SHE as well as zinc both are connected to each other, definitely being more SRP, it should act as cathode. And being less SRP, it should act as anode. But we have arranged here reverse manner. Here SHE we have taken here as anode, zinc electrode we have taken as cathode. That's why here net value, that is a cell potential value, we are getting in negative sign. Cell potential we are getting negative sign means this process is a non-spontaneous process. That is very important. This is the non-spontaneous process. Why? Because SHE should be right side, as well as zinc should be actually left side, but here we have taken in a reverse manner. Because this is a method to find all electrodes potential value. Suppose we are getting a E naught value negative, means this is absolutely non-spontaneous process. Okay, right. Now, when SHE as well as zinc electrodes are connected to each other, now we have to write a cell notation of this cell. How to write cell notation? Very simple. Here, definitely, it is acting as anode. Anode is nothing but oxidation is taking place. Because just now we have discussed that SHE can act as anode as well as cathode. Now here our SHE is acting as anode. Anode nothing but oxidation is taking place. Then the symbol is like this. Then oxidation is nothing but loss of electrons. Therefore, first I am showing the platinum, because on platinum only we are sending hydrogen gas at half H2 at 1 bar pressure, oblique H plus whose concentration is 1 molar. Okay, up to here there is an anode symbol has completed. Then right side we have to write a cathode symbol, there is nothing but a zinc we have to write. Therefore Zn plus 2 whose concentration is 1 molar oblique Zn. And both anode as well as cathode both are connected via salt bridge. That's why both electrodes we have to link by two vertical lines designated salt bridge. And it is acting as anode, we can write a minus sign here. It is acting as cathode, we can write here positive sign. That's all. Like that, standard reduction potential of zinc we have calculated. Similarly, standard reduction potential of copper we have to calculate. See here, E naught again, Cu plus 2 oblique Cu. How much? Standard reduction potential of copper we have to calculate. Again, for that purpose also, same method. Our copper electrode should connect to SHE. In that, our SHE should keep at left side and copper electrode should keep at right side only. Means copper is acting as cathode, SHE is acting as anode. That's why almost the same diagram only we are using here. Now, electrode of course different. That is a 1 molar. It is a copper sulfate solution we are taking. In that a copper rod has dipped. Okay, and the left side as well SHE only has taken, and both are connected with the help of potentiometer. Now when copper as well as SHE both are connected to each other, how much potential difference generated? That is experimentally calculated. Its value is plus 0.34 volts. It is experimentally obtained value only, right? Now again here particularly copper standard reduction potential we have to calculate. We will use as usual again our cell potential formula, that is E naught cell is equals to E naught right nothing but E naught cathode. Who is cathode now? Cathode is nothing but here copper. Cu plus 2 oblique Cu minus E naught anode. Anode is SHE. E naught SHE. Right. And E naught cell value experimentally we have calculated as 0.34 is equals to E naught E naught Cu plus 2 oblique Cu minus, and of course SHE value is assumed as 0. Therefore, E naught Cu plus 2 oblique Cu is equals to plus 0.34 volts. Copper standard reduction potential value we are getting the 0.34. And again here we have to observe one important point, that is E naught SHE. E naught SHE value is 0 volts, as well as E naught copper value. E naught Cu plus 2 oblique Cu is plus 0.34. When we are comparing the both values, and copper definitely bigger value, more SRP value, SHE is a less SRP value. Then according to IUPAC convention, more SRP electrode is acting as cathode generally, and less SRP electrode should act as anode. Here same phenomena is taking place. More SRP electrode we have taken at right side, that is acting as cathode, and less SRP electrode we have kept at anode, left side. That's why net value, that is the E naught value we are getting in the positive sign. E naught value we are getting in positive sign means this is absolutely spontaneous process. In previous case it was negative sign, that was non-spontaneous process, but it is a spontaneous process. Okay. Now again, when SHE as well as the copper both are connected to each other, then we have to write a cell notation. Similarly, same, it is almost similar to previous case. Our SHE is acting as anode, that's why platinum oxidation H2, you can write a half of course, oblique H plus 1 molar. It is a symbol of oxidation only. H2 has converted to H plus. H2 has converted to H plus. That is a salt bridge, and right side will write a Cu plus 2, whose concentration is again 1 molar oblique Cu. That's all. Like this, whatever the electrode may be, all standard reduction potential values can be calculated with the help of SHE value like this. Now, after calculating all these standard reduction potential values, now we have to arrange all the values in the systematic manner. That is only called as electrochemical series. Now we will discuss about electrochemical series. Right, electrochemical series means with the help of SHE, all elements, all electrodes standard reduction potential values we have calculated, and those values will arrange in the systematic manner. That systematic manner itself is called as the electrochemical series. Now, how we are arranging means we are arranging all SRP values from higher value to lower value. We are arranging higher to lower, we have to arrange. That itself is called as electrochemical series. Right. Now I'll take here element. Here I am not giving all electrodes. Generally, regularly repeated electrodes only I am giving here. Element and its electrode reaction, and its concerned SRP value. And here also we will take say 3 columns because we will continue the electrodes. Right. First, the highest SRP element is fluorine. Highest SRP element is fluorine, and lowest SRP element is lithium, whose value is plus 2.87 volts, of course, and here whose value is minus 3.05 volts. Means highest SRP to lowest SRP, we are arranging all the electrodes in the systematic manner. That itself is called as electrochemical series. Here, next we'll take gold, next chlorine, bromine, silver, iodine, and copper, SHE, or we can take hydrogen, of course, hydrogen, then iron, zinc, aluminium, magnesium, sodium, potassium, and of course lithium. Now, here all reduction potential values we are using. That's why what I am doing now, all electrodes reduction reactions I will write. Means fluorine reduction reaction is like this. Fluorine by taking 2 electrons converted as 2F minus. Similarly, gold by taking 3 valency, its valence is 3, by taking 3 electrons convert as AU. Like that, all standard reduction, all reduction reactions we are using here, and even SHE also, H plus by taking electron converted to H2. Dash dash dash. Finally, we will write Li plus electron converted as lithium. All reduction reactions only I am showing. Why? Because we are using a standard reduction potential values. Okay. Then this systematic arrangement itself is called as electrochemical series, right? How to define? In the arrangement of various electrodes. The arrangement of various electrodes. In the, okay, we'll write their values also, of course. Next value is, I am giving just rough values, 1.50, chlorine is 1.36, and bromine is nearly 1.09, silver 0.80, and iodine 0.54, and here copper 0.34. And SHE is familiar, its value 0, iron minus 0.44, and zinc minus 0.76, aluminium minus 1.66, magnesium minus 2.34, sodium minus 2.71, and potassium minus 2.93, etc. And finally lithium minus 3.05. Means all values we have arranged in the decreasing order of their SRPs. This is called as electrochemical series. Now, we will discuss about some applications regarding this electrochemical series. And in that, first if you observe, the highest reduction potential value is related to fluorine. Means in electrochemical series, the fluorine is the only element. Fluorine is the only element which always undergoes reduction. Very simple. If a reduction potential is more, it is always try to undergo reduction only. Next, if a reduction potential value is less, remember, if a reduction potential value is less, then that electrode is not participated in the reduction reactions easily. It prefers for oxidation reaction. I'll repeat once again. If a reduction potential is more, it prefers in reduction process. If a reduction potential value is less, it prefers for oxidation process. First you have to remember this point. Okay. Now, fluorine highest SRP value in entire electrochemical series. That's why our fluorine always undergoes reduction only. An element which itself undergoes reduction is called as oxidizing agent, because oxidizing agent oxidizes others, itself undergoes reduction. That's why we can say fluorine is the strongest oxidizing agent, no doubt in that. Fluorine is the strongest oxidizing agent. Come here, we'll see lithium plus ion. Lithium plus ion, SRP value, standard reduction potential value is very least. Means lithium plus is not having or not showing interest to participate in the reduction process. Why? Because lithium plus is already having a helium configuration. That's why lithium plus is not interested to participate in the reduction process. That's why it is a weak oxidizing agent. We can say weak oxidizing agent. Our fluorine is a strong oxidizing agent. Lithium plus is a weak oxidizing agent because it is not participated in the reduction reaction very easily. Right. Next. F2. Next we'll see F minus. F minus. See here. If you observe a reverse reaction, particularly the reverse reaction becomes oxidation. Forward reaction is reduction, means of course backward reaction is definitely oxidation only. And if 2 F minus ions, by losing the 2 electrons, if converted as F2, now reduction potential value becomes reverse, it becomes oxidation potential value. That's why minus 2.87 is oxidation, that is a standard oxidation potential of F minus. If you observe the value, F minus standard oxidation potential value is very least. That's why our F minus is not interested to undergo oxidation. Why? Because F minus already having a neon configuration, it is a stable species. That's why it is not it is not undergoing oxidation process very easily. That's why we can say F minus is a weak reducing agent. F minus is a weak reducing agent. Similarly, if you see lithium, okay. Now, if you observe the lithium property, again you have to see backward reaction. Backward reaction is lithium converted to lithium plus electron. Here standard reduction potential is minus 3.05, means it's a standard oxidation potential. Why? Because I have shown here oxidation reaction. Its oxidation potential value is plus 3.05. What it indicating means lithium standard oxidation potential is highest in electrochemical series. Lithium standard oxidation potential is highest, means lithium easily participated in the oxidation reactions. Lithium participated in oxidation reactions very easily. That's why lithium is a strong reducing agent, because reducing agent reduces others and itself undergoes oxidation. Our lithium is a strong reducing agent because lithium easily participates in oxidation process because its oxidation potential is highest. In electrochemical series, remember fluorine reduction potential is higher, and lithium, not lithium plus, lithium oxidation potential is higher. That's why fluorine is a strong oxidizing agent and lithium is a strong reducing agent. That's why we can also say like this: in electrochemical series, oxidizing tendency decreases. Oxidizing tendency decreases in electrochemical series. Okay. It is one of the application of electrochemical series, and next some more applications also we'll discuss. Right. If you observe particularly SHE, standard hydrogen electrode, whatever the elements are present below hydrogen, and these elements are highly reactive comparing with SHE. I'll repeat once again. Whatever the elements which are present below hydrogen in electrochemical series, those elements are highly reactive comparing with the hydrogen. So what they will do then? Any element if you take, and these elements will displace hydrogen from its solution, nothing but from its acid. For example, say zinc and has reacted with a hydrogen contained solution, that is HCl. Balancing purpose we have taken 2. Now what happened? This zinc metal is coming and removing this hydrogen. Zinc is coming and displacing hydrogen and convert as ZnCl2 plus hydrogen gas escapes like this. Means here zinc element is below hydrogen in electrochemical series. That's why this below element is coming and displacing above element in electrochemical series. Why it is happening? Very simple. Then hydrogen and zinc both are compared to each other. Then hydrogen SRP value is 0, zinc SRP value is minus 0.76. Out of these two, whose reduction potential is more? Definitely SHE reduction potential only more. So when both are connected to each other, which electrode should undergo reduction as well as which electrode should undergo oxidation? Definitely SHE only should undergo reduction and zinc undergoes oxidation. Same thing happens, same phenomena is taking place. See here, zinc right now elemental state. After displacing hydrogen converted to Zn plus 2, zinc oxidation state is plus 2. Increase in oxidation state, nothing but oxidation is taking place. Means zinc undergoing oxidation. And HCl, hydrogen oxidation number is 1. Here 0, decrease in oxidation number, nothing but a reduction. Being a more SRP, hydrogen undergoing reduction. Being less SRP, zinc undergoing oxidation. That's why whatever the element may be below hydrogen in electrochemical series are highly reactive. They can come and displace hydrogen from its solution. Next, suppose the element which is present above hydrogen. The element which is present above hydrogen, say for example copper. Same reaction if occurs with copper. Let's see what happens. Cu is reacted with HCl converted as CuCl2 plus hydrogen. We'll observe what happens. Here when copper as well as hydrogen both are compared to each other, copper SRP is higher than SHE. Means when both are connected to each other, copper should undergo reduction, hydrogen should undergo oxidation. Here what happens, we'll see that. When the copper is reacted with HCl, being elemental state oxidation number 0 and here oxidation number of copper is plus 2, here increase in oxidation number, here oxidation is taking place and here plus 1 converted to 0, here reduction is taking place. It is completely reverse phenomena is taking place. Being more SRP, copper should undergo reduction. Being less SRP, hydrogen should undergo oxidation, but here reverse phenomena is taking place. Copper undergoing oxidation, hydrogen undergoing a reduction. That's why it is a non-spontaneous process. Non-spontaneous process. Here we can say it is a spontaneous process. Because here reactions are taking place according to their SRP values. But here reactions are not taking place according to their SRP values. If reactions takes place according to SRP values, we can say it is spontaneous. If reactions are not taking place according to their SRP values, then it is a non-spontaneous process. Right. That's why now here one general statement we can tell. As far as metals are concerned, particularly remember, as far as metals are concerned, any below metal can displace any above metal from its salt solution. I'll repeat once again. As far as metals are concerned, any below metal can displace any above metal in electrochemical series. Say for example, like iron, Fe. If I take reacted with, for example, Zn reacted with Fe, SO4, suppose. Zinc value is minus 0.76, iron value is minus 0.44. It is a below metal, it is above metal, remember. In electrochemical series, it is a below metal and it is above metal. Any metal which is below can come and displace any metal which is above from its salt solution. That's why this zinc will come and it will remove iron and convert it as ZnSO4 plus Fe. Why it is happening like this? Same phenomenon again. Being less SRP, our zinc should undergo oxidation. Being a more SRP, iron should undergo reduction. Same phenomena is taking place. Zinc elemental state oxidation number is 0 and ZnSO4 oxidation number is plus 2. 0 has converted to plus 2, increase in oxidation state. Then zinc undergoing oxidation and FeSO4 iron oxidation number is plus 2. Your elemental state is 0, iron undergoing a reduction. Means Here reactions are taking place absolutely according to their SRP values. That's why this reaction also we can say spontaneous process. But very important point is, as far as non-metals are concerned, the process is completely reverse. Means above non-metal can displace below non-metal from its solution. For example, we'll take here chlorine as well as bromine. It is above non-metal, it is below non-metal. When a Cl2 reacted with a KBr solution, it is above, well, because its potential value is more, SRP value more, its SRP value is less. Then both are reacted to each other. Now chlorine will come and remove bromine, and you will get KCl plus Br2. Of course, balancing 2, and here also we write 2. As far as metals are concerned, below metal can displace above metal from its solution. As far as non-metals are concerned, above non-metal can displace below non-metal from its solution. We will see here. It is above non-metal, is coming and displacing a below non-metal. Why it is happening? Same phenomena. Then here, being more SRP, chlorine should undergo reduction. Being less SRP, bromine should undergo oxidation. Whether that happens or not, we will see then. Right now, molecular state oxidation number is 0, and here chlorine is -1. 0 has converted to -1. It is a reduction process. And here KBr, Br -1 oxidation number, molecular state is 0. This -1 has converted to 0. Increase in oxidation state, it is oxidation process. Means here chlorine as well as bromine, according to their SRP values only reactions are taking place. That's why it is absolutely spontaneous process. That's why what we can tell then, as far as non-metals are concerned, above non-metal in electrochemical series, of course, above non-metal can displace below non-metal from its solution. Right. Next, in electrochemical series, we can calculate EMF value, that is a cell potential value, by taking any two electrodes. By using any two electrodes, we can calculate cell potential values like this. Example purpose, I am using say E0 Zn plus 2 oblique Zn value minus 0.76. Minus 0.6 means it is a standard reduction potential of zinc electrode. Now I am taking any other electrode, that is our wish, any one we can take. Then Al plus 3 oblique Al, aluminium. Its value minus 1.66. Okay. Then if these two electrodes are connected to each other, then what is the net cell potential we have to calculate. Right. First we have to observe which SRP value, which electrode SRP is more. Definitely zinc reduction potential is more and aluminium reduction potential is less. When both are connected to each other, which is acting as cathode, which is acting as anode, blindly you have to remember, more SRP electrode will act as cathode, less SRP electrode will act as anode. That's why E0 cell potential is equals to E0 cathode minus E0 anode. Cathode is nothing but higher SRP electrode. Anode is nothing but lower SRP electrode. Therefore, higher SRP electrode is a zinc minus 0.76 minus anode lower SRP electrode, that is a minus 1.6 minus 1.66. Therefore, minus 0.76 minus of minus plus 1.66. Then if you calculate whatever the value you will get, that is a cell potential, that is a net cell potential of these two electrodes. Some more examples we can take. Next, another example. One is E0 Cu plus 2 oblique Cu plus 0.34 volts, E0 Ag plus oblique Ag plus 0.80 volts. These two electrodes I have taken, and both these electrodes again I am connecting to each other. Again with the same salt bridge process completely remains the same. When both electrodes are connected to each other, then again definitely cell potential will be generated. How much potential generated we have to calculate. Again we are having a formula. E naught cell is equals to E naught right minus, E naught cathode minus E naught anode, or E naught right minus E naught left. Then out of these two, which electrode is anode, which electrode is cathode? Blindly you have to remember, higher SRP electrode is cathode, lower SRP electrode is anode. Out of these two, our silver being higher SRP is acting as cathode. Therefore, first we write as 0.80 minus 0.34, and if you do the subtraction, whatever the value you will get, that is a cell potential of this galvanic cell. And one more example we will take. First example related to both minus values. Second example is related to both plus values related cell. And third one is a plus, one is minus. Say one copper electrode as well as one zinc electrode, minus 0.76. Again we have to go back to Daniel cell. In the Daniel cell also we have taken copper as well as zinc only. Same electrodes have used. Then here out of these two, copper being more SRP, we have to keep right side acting as cathode, and zinc being less SRP, we have to keep left side, that is acting as anode. Therefore, total cell potential E naught cell is equals to E naught cathode minus E naught anode. Here, which is cathode? More SRP, that is 0.34 minus of minus less SRP value. We are getting already known to you its potential value 1.1 volts. Remember, if E naught cell value we are getting in positive sign, then we can say that this cell reaction is spontaneous process. If E naught value will get a negative sign, we can say that cell is non-spontaneous. Means if a cell construction occurs according to their SRP values, I'll repeat, if a cell construction occurs according to their SRP values, means less SRP acting as anode and more SRP electrode acting as cathode, like that if you arrange, definitely your E naught cell will be positive and that cell is a spontaneous process. Suppose if you arrange in the reverse manner, then definitely E naught value will get in negative sign. Negative sign means that is a non-spontaneous process. Okay? Then with this we'll stop this video. In the next class we'll discuss about some examples related to our electrochemical series. Thank you. Bye.